All right. Good morning, guys. For today session, today we're looking at enzyme inhibition. All right. So when we talk about enzyme inhibition, it is actually the process of decreasing the rate of enzymatic reaction. So the process of decreasing the rate of enzymatic activity. All right. So this is what we mean by enzyme inhibition. Now, before we continue, I would like to say something, then we proceed. In our human body system or in vitro inside the living system, we have so many metabolic activities happening, and these metabolic activities, most of them are feasible. Now, when we talk about they being feasible, it simply means they are spontaneous. All right, so they are spontaneous in the sense that they do not need external factors like energy to drive them. So they are spontaneous, they occur naturally. Now, these metabolic activities are the activities that happens to actually sustain life. So we having so many metabolic activities in our living system actually affects or brings about a good living system. Where it is this activity that will bring about the release of energy and other essential things that the body needs for survival. Now, these activities or most of these activities in the system are feasible or spontaneous, meaning that they occur naturally. But then they are so most of them are so very slow. They are having a very slow rate, such that if there is no action of enzymes, it will take about months, years, so many years before they will even happen. So let's take an example like the glucose. Now, when you bring, you all know glucose burning in excess oxygen to bring out energy. All right, so this reaction, when it happens in vitro, when you talk about it happening in vitro, it simply means it's happening outside the living cell. So you performing it in the, let's say, outside in the laboratory or anywhere outside the living cell. That's what we mean by in vitro. So outside. Now, when this reaction is in vitro, when you have your glucose sample down and it is being exposed to oxygen, it will take so many years, in fact, weeks, months, years, and you will not see any reaction happening. Alright, but then when you take this same glucose to the living system, when you take it in vivo, when you talk about in vivo, the reaction happening inside the living cell. So when it goes in vivo, with the help of these enzymes, the enzymes are able to speed up the rate even at like billions folds. So enzymes can speed up rates like billions folds, and they do that within seconds, okay? And so they're able to speed up the rate such that the breakdown of glucose in the oxygen will release the energy or the amount of energy needed by the system to for life to continue. So enzymes are so useful to our living system and to other living organisms as well. Now, today we'll be looking at certain factors that inhibit or decrease the rate of this enzymatic activity. And that's where we have our topic for today, enzyme inhibition. So on the board, we said enzyme inhibition is a process of decreasing the rate on enzymatic activity. Now, we will start from, basically we have two types of enzymatic inhibition, okay? But then before that, you see me telling you the importance of enzymes and then later on telling you that inhibition decrease the rate of the enzymatic activity, you might be thinking inhibitions or inhibitors are not useful. But then as you proceed, you realize that some of them are very useful whilst others too are not useful. So before you go to the two types of inhibition, let me give you these two enzymes, then we look at something else. So we have something called transpeptidase, and we have a drug called penicillin. Okay, now this is an enzyme. Sorry, yeah, this is an enzyme. Okay, sorry, this is an enzyme, And this enzyme actually is found in bacteria. And what they do is that they help the bacteria to produce their cell wall, okay? And when you have an inhibition or an inhibitor, which will come to decrease the activity of this enzyme, it will help decrease the rate at which the bacteria produces its cell wall. And when this bacteria finds itself in the living system, you know the living system also have its own soldiers like the immune system that will release antibodies and the rest to fight foreign materials like this bacteria in your system. And so if you have inhibitor that will decrease the rate, it will decrease the rate at which the bacteria produces its cell wall. And so when this bacteria is found inside the living cell, the immune system will be able to easily eradicate such bacteria from your living system. So this inhibition, when you go into them, realize that they are important, like they are very useful, like the example I've stated here. So for the transpeptidase, when you bring in the inhibitor, it's coming to decrease the activity of this enzyme such that the bacteria will not be able to produce a cell wall that gives it resistance. Okay, we also have penicillin, and we all know what penicillin is. Okay, it's an antibiotic that helps, and it also decreases the rate of the enzymatic activity. Now, so these are some of the useful inhibitors that we have. Now, we also have an inhibitor known as the nerve gas. So before we go to the types, I just want you to know certain usefulness and other usefulness of inhibitors and other inhibitors that cause adverse effects to our living system. And an example is the nerve gas. The nerve gas is actually a chemical substance that disrupts the mechanism or the mechanism that happens for nerves to transfer messages through neurotransmitters to targeted organs like the organs or to other nerves, okay? And so this nerve gas, when you have the nerve gas coming into the system, it is actually coming to decrease the rate by disrupting the mechanism such that there is this enzyme known as acetylcholine stearate. Right. So this enzyme acetylcholine stearate is the enzyme that catalyzes the breakdown of acetylcholine, which is a neurotransmitter. Okay. So when I talk about neurotransmitters, I simply mean those that carry the messages to the targeted organs from the nerves. Okay. So this nerve gas, which is acting as an inhibitor, is coming to decrease the rate. It's actually coming to stop that reaction where the acetylcholine stearate breaks down this acetylcholine for them to be used as neurotransmitters to transmit messages to other targeted organs for the human body system to function very efficiently and properly. So you can see this nerve gas, it is not useful, okay? So they even use this technique to produce poisons. So you can see you have inhibitor helping the living system, and you also have inhibitor which is being used as a poison to also kill living system. So these are some pros and cons of these inhibitors. So not all inhibitors are useful, and not all inhibitors too are also harmful. Some are useful, others too are very dangerous, like the nerve gas. Okay, so today we'll be looking at the types of inhibition, and we have two types. We have the first one known as the irreversible inhibition, and the two we have the reversible inhibition. Okay, so basically these are the two types of inhibition: irreversible inhibition and then reversible inhibition. Now from the name, I think it is self-explanatory. All right, so
Let's go.
okay, so we are still talking about the irreversible inhibition, and I'm saying that it's even self-explanatory from the word irreversible. So this irreversible inhibition actually contains the inhibitors that actually binds tightly. So they bind tightly to the enzyme surface such that applying them to certain conditions will not be applicable to dissociate the complex that will be formed. Okay, so when the inhibitors bind with the enzyme to form the enzyme inhibitors complex, you'll not be able to subject them into certain conditions to dissociate back that complex. So they are irreversible, and they normally bind through covalent bonding. Okay, you can as well have other irreversible inhibitors that can bind through other non-covalent bonding. Okay, but then most of them bind through covalent bonding, and they bind very very tightly. So that is for the irreversible inhibition. And we have types of irreversible inhibition, but then today's content will focus on reversible inhibition and the types under reversible inhibition. Okay, so let's focus on reversible inhibition. Now, reversible inhibition is actually the opposite of the irreversible inhibition, as the name implies, reversible, meaning that after they binding to form the complex, you can subject them to certain conditions to actually dissociate the complex that will be formed after the binding. Okay, so that is for the reversible inhibition. Now, under the reversible inhibition, we have three types of reversible inhibition. The first one we'll be looking at is the competitive inhibition. Good. Competitive inhibition. Now, the competitive inhibition actually involves the inhibitors that bind to the active sites of the enzyme or free enzymes. Okay, so I want you to take note of the key terms I'm using. They only bind to the active sites of the free enzyme. Okay, so I'll be putting certain diagrams on the wall for us to appreciate what I mean by that. Now, another thing you have to note under the competitive inhibitors is that the competitive inhibitors actually resemble the substrates in terms of their structures. So we'll be looking at an example like the malonate or the malonic acid, which actually acts as a competitive inhibitor to decrease the rate at which succinate dehydrogenase comes into contact with succinic acid to form fumaric acid or fumarate. So we'll be looking at examples soon. But then let me try and draw something. So this is an enzyme. This is an enzyme. And this is the inhibitor. And this is the substrate. So when you look at these three things, this is enzyme, inhibitor, substrate. Now this inhibitor is a competitive inhibitor. And let's see what it will do to the enzyme. Now we have a free enzyme. It is free when it is not in relation, it's not binding to any of the two components here. This is the substrate. Looking at the substrate and the inhibitor, I realize that they are kind of similar in structures. Okay, so what will actually happen is that this inhibitor, normally the competitive inhibitors are having higher affinity towards the active sites of the enzyme than the substrates themselves. Okay, so when you have relatively in terms of concentration, if the concentration of the substrate is not very very high compared to the inhibitor, you have the inhibitor binding first to the active sites of this. So this will bind. So we'll be having the inhibitor like this here to form enzyme inhibitor complex. So this is what I mean by the complex. Okay, and after it's binding to the active sites, there is no any other site for this substrate to bind. Now bear in mind, these substrates do not bind to the allosteric sites. They bind to the active site. That's the site you find the binding groups and the enzyme. That's where the enzymatic activity actually happens. Okay, so when you have a competitive inhibitor that actually replaces that site, then this substrate will not get any place to bind. So now I made mention of an example like malonate. Let's see what actually happens there. So we have succinic acid, okay, which is CO minus CH2 CH2 minus. Now this is succinic acid. When it is in the ionic form, as I've done on the board, it is called succinate. Okay. When it is, you bring the H, then you can call it succinic acid. When it is in the ionic form, it is succinate. Now this succinate undergo redox reaction, okay, and it is being catalyzed by the enzyme known as succinate dehydrogenase. And this succinate dehydrogenase falls under the class 1 enzyme known as the oxidoreductases. Okay, good. So succinate dehydrogenase. Succinate from the fact that it acts on the succinate substrate. and they are hydrogenase from the fact that it removes hydrogen from the substrate. Okay, so there is removal of two hydrogens here, so you can put this here to form the product known as fumarate. Alright, so if there is the presence of H here, you form the fumaric acid. But then if it is in the ionic form as I've done on the board, then that is the fumarate. Okay. So this is the reaction happening where you have this substrate binding to the active sites of the succinate dehydrogenase, and the succinate dehydrogenase through its enzymatic activity or reaction removes two hydrogens from adjacent carbons here. So it removes one hydrogen from here, one hydrogen from here to form a pi bond here. Okay, this is organic chemistry. So after forming the pi bond here, you form a final product known as the fumarate. But then we have this competitive inhibitor known as the malonate. Okay, malonate. And this is how the structure looks like. So because of the 8, it means that it is in the ionic form. Okay, so CH2. Okay, now let's look at this structure here as our inhibitor, the malonate. You can see comparing the inhibitor to the substrate, you can see they resemble in terms of their structures. The only difference is a methylene group. Okay, this is a methylene group. So the only difference between the two is the methylene group here. Aside that, they are equally the same in terms of the two carboxyl groups here and the one methylene group here. Okay, so you can see I earlier on said that for the competitive inhibitor, one of the things you have to note is that the inhibitors are actually resembling, or they actually resemble the substrates in terms of their structures. Okay, so you can actually see it here. So what will actually happen is that instead of, I also said that the inhibitors have high affinity towards the enzymes and the substrates. So when there is this reaction and there is this inhibitor present, it is actually this one that will actually bind with the active sites of this succinate dehydrogenase. And let's see what will happen. When it binds to the active sites of the succinate dehydrogenase, then it means that this one will not have any place to bind with. Okay, but then let's see, someone might ask, if we have an inhibitor having similar structure as this and it is successfully binding with the enzyme, then why don't they just proceed to give us our final product? Now when you look at this here, the malonate doesn't have adjacent carbons that contains hydrogens for them to be deprotonated to form the pi bonds. Okay, so you can see we have only one methylene group here. When the enzymes take one hydrogen here, it will not get any other adjacent carbon to extract hydrogen from it. Okay, so with this, you see it cannot take any hydrogen. So as a result, this reaction doesn't occur. So that is the action of these inhibitors. When it comes to bind with the succinate, the hydrogenase, the active site of it stops the reaction because the enzyme will not be able to remove two hydrogens from adjacent carbons because there is only one carbon in the middle here. And you can't take two hydrogens from one carbon to form pi bonds on the other two sides of the bond. Okay, so that is what actually happens. So this is for competitive inhibition or for the inhibitors. Now, one of the main things I want you to pay attention to here or to remember under the competitive inhibitor is that the competitive inhibitors only binds with the free enzyme. Okay, as we proceed, you understand what I mean by that. So the competitive inhibitors, they only bind with the free enzyme. So what I actually mean is that the competitive inhibitors in the reaction will bind when there is free enzyme, not when there is a complex between the enzyme and the substrate. Okay, now there is one way of actually decreasing or stopping the action of the inhibitor, and that way is by increasing the substrate concentration. So when you increase the substrate concentration, even though the inhibitors in the actual sense have higher affinity towards the enzyme than the substrate, increasing the substrate concentration will actually mask the effect of the inhibitor such that you have your products forming as your fumarates. Okay, so one of the ways of stopping the action of competitive inhibitor is by increasing substrate concentration. So this is it for competitive inhibition. Note, it only binds when there is free enzyme. Now let's go to the next inhibition known as the second inhibition known as the uncompetitive inhibition. So B, sorry, one thing I have to do. Now, in our last video, I was explaining the Michaelis-Menten's equation using the plots, okay? And Michaelis and Menten gave us a plot that looks like this, or that looked like this, okay? Now, studying graphs that are not regular is very, very difficult. So we have this man who also came with a different plot, but then it is actually the same thing, but then he took the inverse of these two, and that plot is called Lineweaver-Berg's plot. Lineweaver-Berg's plot. Okay, so this Lineweaver-Berg's plot is just a modification to the Michaelis-Menten's plot. Okay, so what they actually did is that they find the inverse of this, that's 1 over v. They plot this inverse of the substitute 1 over s. Okay, 1 over s. So when you do this, instead of this going this way, to rather go this way. Okay, so you see this is a straight line, and studying straight lines are very, very simple to get it. Okay, so we'll be looking at the graphs that are related to competitive inhibitor. As we proceed, I'll be giving you graphs that are related to this inhibition, so that in case you see it anyway, you'll be able to understand. I'm very sure you can get a question that will give you a graph and will ask you which type of inhibition or inhibitors were actually present. So when you see such graphs, you should be able to interpret. Okay, so we'll be looking at the graphs of this inhibition under the Lineweaver-Berg's plot. We also have the Hinswolf plot. Okay, that one too is the same thing, but then it uses substitute over green, then also something else. So let's see. So under them, before we go to the uncompetitive inhibitor, let's look at the graph for the competitive. Okay, the graph for it. So this is actually how it looks like. So we are taking the inverse of the rate, then the inverse of the substrate concentration. Here is 0. Now when there is no inhibitor, this is the line we are getting. When there is inhibitor, which is a competitive inhibitor, this is what we will be getting. Okay. So this is minus I, meaning that no inhibitor. And this is positive I, meaning that there is this competitive inhibitor. So this is the graph for competitive inhibitor. When you watch here, you can see that they have the same y ordinates. Okay, so this here is equal to 1 over v max. This side is equal to 1 over v max. It means that the competitive and the when there is no inhibitor, they both have the same 1 over v max. So in a question, they can ask you to find for v max after plotting your graph, and you just come in to find the inverse of this, you get your v max. Okay, right. And here for the inhibitor, its x ordinates, that's its s ordinate here, or its s mark here on the s axis, will be equal to minus 1 over km. Now I'm pretty sure you understand what the km is, because in our last video that is what we dealt with. Okay, the km is the Michaelis constant, and I explained in my last video. So if you want to understand the Michaelis constant, well, you can check up on my last video. So this is actually the value for this one when there is no competitive inhibitor. This is it for it. Okay, all right. Now when there is competitive inhibitor, it is also going to be 1 over km, apparent km. Okay, but then you are going to multiply it with 1 plus the concentration of the inhibitor over the ki. Okay, so these are the things you need to know for this competitive inhibitor. This is the plot for it. You can have more than one competitive inhibitor, so that one will also go here like that. So we can have more than one. This is only when you have only one. Okay, so just note this is minus 1 over km. So in the question, they can ask you to find for km. You just have to locate this side and find for the negative reciprocal of it to get your km for that. And you can use the same idea to calculate for all these things here. So this is it for competitive. Without wasting much time, let's go to uncompetitive inhibitor. Alright, so B. Uncompetitive inhibition. Now the uncompetitive inhibition it actually involves the inhibitors that bind only to the complex. So one of the main thing I want you to focus here or to pay attention here is that they only bind when there is enzyme substrate complex. So when there is this enzyme substrate complex, that is where the uncompetitive inhibitors can bind. Now there is this thing called allosteric sites of enzymes. Okay, so as I explained, you understand why I'm saying that they only bind when there is this complex. Now let's take this enzyme for instance, and this is the substrate, this is the enzyme, and this is the uncompetitive inhibitor. Okay. Now, when the enzyme is there like this is the free enzyme. The inhibitor, which is the uncompetitive, will not come and bind with the active site of the enzyme. They don't bind with the active site. But then this substrate is what can actually bind with the active site. So the substrate will come in to form the enzyme substrate complex, also known as the saturated enzyme. So when you have this complex, at times when they bind with the active sites, they induce conformational changes. Okay, so when they induce conformational changes, they create certain allosteric sites. They create certain allosteric sites on the surface of the complex, such that it will have this inhibitor coming to bind to that allosteric site. So you have this coming here to form this. So you'll be forming this intermediate. Now this intermediate will also, when you have the enzyme substrate inhibitor complex, when the complex binds to the allosteric site, they also induce further conformational changes such that they will try to change the shape of this active site to propel or release the substrate to decrease the rate of the activity of the enzyme. Okay, so what I said was that they only come when we have formed the complex, and the complex induce allosteric sites for these inhibitors to actually join. Okay, that's what we mean by uncompetitive. They don't compete for the active site. They only come when there is a complex, and the complex has induced allosteric sites, a temporal allosteric sites for them to come. When they come, they also come and induce conformational changes to change back the structure of the active site to actually release the substrate so that they will do their action. Okay, so that is it for the uncompetitive inhibitor. So one of the main things I want you to notice what I earlier on said, that they only bind when there is enzyme substrate complex. Good. Okay, so let's look at the graph for it. So the graph is very simple. So as I said, there is 1 over V, 1 over substrate concentration. Uncompetitive inhibitor is just this. They don't cross. So this is when there is no inhibitor. This is when there is inhibitor. So this is a graph for uncompetitive inhibitor. You know what these values will be. Okay, I've already explained it. Because of time, I just want to run over it very, very quickly. So this is for uncompetitive inhibitor. So we are done for it. This what happens, they only bind when there is this. Now when this complex forms, they induce allosteric sites, which also allows the binding of the uncompetitive. And the uncompetitive can also continue with the further inducing of the structure, such that they change the shape of the active site that is already in bondage with the substrate to propel back the substrate so that they will decrease the rate. Okay, so this is what is happening for the uncompetitive inhibition. Now let's go straight to the last one, known as the on non-competitive inhibition. Non-competitive inhibition. Don't let these two terms confuse you. We have uncompetitive inhibition and non-competitive. So non and on. Non and on. Okay. Now for the non-competitive inhibition, they involve the inhibitors that we have some enzymes that actually they are allosteric enzymes. Okay, when I talk about they being allosteric enzymes, I mean they actually have permanent allosteric sites. Aside they having the active site, they have permanent allosteric sites. Like what we just did, the uncompetitive, where I told you that there is no allosteric site, but then the complex will induce allosteric sites. For the non-competitive, what you will see is that the enzymes, you can get enzymes that are allosteric enzymes. So they actually have the permanent allosteric site. So let's say we have this enzyme. This is the active site, this is the allosteric site. So this enzyme is an allosteric enzyme. So it will allow the substrate to come here. It will allow the inhibitor to come here. And this inhibitor, which is the non-competitive, will also when they bind with the allosteric site, they induce conformational changes. Okay. They also want to get some shade. So there will be some kind of movements that will change the shape of the active site to decrease the rate. Okay. Now, one of the main things I want you to note under the non-competitive inhibitor is that they can either bind to free enzymes or they can bind when there is complex. So note the differences we brought so far. Let me say it again. Under the competitive, we said they only bind with free enzyme. Under the non-competitive, we said they only bind with the complex. Now, for the non-competitive, they can either bind to free enzymes or to the complex. And the reason is that they can bind to free enzyme because when the free enzymes are there, they are not going to bind with the active site, okay? But then when the free enzymes are there, I told you those enzymes are actually allosteric enzymes. So they have the permanent allosteric sites for the binding of this non-competitive. And also when there is a complex, there is still this permanent allosteric site. Okay, so it is because of this permanent allosteric site that allows them to bind either to the free enzymes or to the complex. So that is all for the non-competitive inhibitor. So they either bind to free enzyme or when there is enzyme substrate complex. So that is what you have to note under the non-competitive inhibitor. So the graph for it will just be 1 over V. So we are looking at the Lineweaver-Burks plot, 1 over substrate concentration. We have this, we have this. So whether there is non-competitive or not, you are still going to get the same S value here, which is minus 1 over K. Okay. Here is when there is no inhibitor. Here is when there is a non-competitive inhibitor. So guys, this is actually what I want you to note for the 3 types of inhibitors under reversible inhibition.
One.
Okay. So that is it for the 3 types of inhibitors under the reversible inhibition. Maybe in my next lesson or in my next video, I might talk about the types of inhibitors under the irreversible inhibition. Okay. But then guys, for today, that is all for today. The types of inhibitors under reversible. So if you look at competitive, uncompetitive, then the non-competitive. Competitive bind only when there is free enzyme. Uncompetitive bind only when there is complex. Then non-competitive can either bind whether there is free enzyme, when there is either a free enzyme or a complex. So that is it for today. Okay. So on this note, subscribe to the channel. Okay. Don't just watch it. You subscribe, you support, you like, and you also share as well. You share to your statuses, your groups, for other friends to also enjoy or also benefit from today's lesson. On this note, see you in my next video. Thank you.